This second Paper 3 revision video will go through our physical fieldwork that we did in the Upper Goyt Valley. Watch the first video too, as it goes into more detail about our human fieldwork in New Islington. So for our physical, we studied the Goyt River and one of its tributaries called Deep Clough in its upper course between Macclesfield and Buxton. You need to know what we did and why we did it, that's your justification, and also to evaluate what we did to say whether the results were accurate. You need to know what we investigated, the methods, how we presented and analysed the data. So firstly, you need to remember the title, How Does a River Change as it Flows Downstream? The River Goyt flows north from its source near Goyt's Moss, through a couple of reservoirs, Whaley Bridge, Marple, and eventually joins the Mersey in Stockport. Again, we need to justify the location, to give reasons why this is a good location to study how a river changes downstream. Firstly, it's accessible by a footpath from a car park. Secondly, there are some tributaries, so the volume of water in the river will increase over a small area. And thirdly, the river here is in the upper course, a narrow, steep-sided valley, so it's likely to be shallow enough to wade in and take measurements safely. We need to know what the risks were and how we minimised them. The valley sides were steep, so we stuck to the paths. The river was deep in places, so we only went in when it was shallow enough so we didn't fall in. The rocks were slippery, so we wore footwear with a good grip. And the grass was dry and could catch fire, as it had done a couple of weeks previously, so we did not light matches and were careful not to leave glass around. We broke our main title down into 3 sub-questions. Firstly, does the velocity of the river change as you go downstream? Velocity is the speed of water going down per second. Secondly, does the discharge of the river increase downstream? Discharge is the amount of water passing a point per second. And thirdly, does the shape of the bedload change as you go downstream? So now we need to think about how we chose where to collect our data. In other words, to justify our sampling strategy. We could have chosen to collect our data at random sites. If we had done that, we might have chosen some sites too close together to show a difference that we were trying to prove in our title. Ideally, we would have collected our data systematically along the 50-kilometre stretch of the River Goyt at regular intervals, but this would have taken a lot of time and the river may have been too deep lower down to measure it safely. So we decided to use a stratified sampling strategy and to collect data at 3 sites that look different to each other. The first one being Deep Clough, a small tributary with a small catchment. Site 2 being on the River Goyt, just before it's joined by Deep Clough, that's a larger catchment, and Site 3 being after the confluence of the 2 rivers, which has a larger catchment area. This meant we would be able to see differences in discharge and velocity, and we also used secondary data collected at different points further up and further downstream on the Goyt to give more data. We need to be able to describe, justify and evaluate our methods, to link what we did to the questions we were trying to answer and understand what might have influenced the accuracy of the results. The first thing we did was to measure velocity so we could see if it increased downstream. At each site we put a hydroprop into the water at 3 points across the width and timed how long it took for the impeller to spin along to the end of the rod. The impeller thread was 3.2805 metres, so we could then calculate the velocity, and we calculated the average velocity for each site. This was primary stratified data we collected ourselves at 3 selected sites. So now we need to evaluate if this method produced reliable results. Well, the water was too low in places at the sides to turn the impeller, as there had been little rain, so this made the river look slower than it was. So to overcome this, we tried measuring surface velocity by timing how long it took for a dog biscuit to float downstream 10 metres. Generally, the biscuit floated on low water, so it was a better method, but sometimes it got stuck by boulders. We also used secondary data when we got back to school, taken at sites higher up the Nars and extending another 20 kilometres downstream. This let us see if the velocity changed over a wider area than we were able to measure in a day. So their data was probably more accurate than ours, as it covered more sites and wouldn't have been as affected by anomalies as ours might have been. However, it wasn't directly comparable to ours, as it was taken at a wetter time of year when the discharge and the velocity would have been greater. The second questions we were trying to ask is whether discharge increased as you went downstream. Discharge is the amount of water passing a point each second, and we can measure that by measuring the cross-sectional area in meters cubed and then multiplying that by the velocity in meters per second to give the amount of water flowing past, measured in cubic meters or cumex. So each site we measured the width using a tape measure, and we used a ruler to measure the depth at 5 points across the width to give an average depth. So did it produce reliable results? Well, we chose sections we could stand in and avoided the deepest parts and boulders, so the cross section didn't always represent the whole area. Finally, to see if the bed load got smaller as the river flows downstream, we categorised the shape of stones using a Powers angularity table. We selected stones randomly by putting a ruler in the water every metre in a 10-metre stretch and taking one stone out. It was difficult to measure larger boulders, however, so we did end up selecting the smaller stones to measure, so stones may have actually looked a little bit more rounded than they were in reality. So let's turn our attention now to how we presented our data. And again, we need to be able to justify and evaluate our presentation methods. We used our secondary data of velocity over the 9 sites on the river going downhill, and we plotted these 2 variables on a scatter graph. Scatter graphs are brilliant at showing if there is a relationship or correlation between 2 variables, in this case distance and velocity. So it lets us answer our question about whether velocity increases downstream. And then we can draw a line of best fit which goes near or through as many lines as possible. And it shows how strong this relationship is and shows up any anomalies. So if those points are very close to the line, there is a strong relationship, and if they're quite a long way from the line, the relationship is weaker. And of course we can see if it is a positive or negative relationship. So we need to evaluate this data presentation method. You can see it's very visual, it's clear to see a positive correlation as distance increased, velocity increased, and it's clear to see that this relationship was particularly strong higher up the valley. It's also clear to see an anomaly at 16 kilometres at Marple Weir because the weir blocked the river and caused the water to back up and slow down the flow. We calculated the discharge by multiplying the cross-sectional area by the velocity, and then we presented this by colouring in 1 square on a grid of 100 squares for each cubic metre of water. We then put the grids next to each other on a map to geolocate it. This presentation method made it easy to visually compare sites, and by putting it on a map we could see spatial change, how the amount of water increased as you moved down the valley, which is what we were trying to prove. Finally, we presented our results of pebble angularity using a stacked bar graph for each site. This again helped us see changes very visually as you can compare changes in colour categories across the 3 bars plotted side by side. You can see the angular pebbles shown in orange decreased and rounded pebbles shown in grey increased. Pie charts would have also had a similar impact. So what did we find? Does the River Goyt change as it flows downstream? Yes, the discharge increases because the river has more water in it. Relatively less of that water is being slowed by contact with the river channel, and therefore its velocity gets faster too. And because it flows faster, stones bash against each other and are eroded by attrition to become rounder. So yes, the Goyt does change as it goes downstream. So finally, we need to evaluate how accurate our results were. And what did we do to make sure that our results were reliable? Firstly, we used an average of five measurements across the river to reduce any inaccuracies, and we also stood downstream of the impeller so we didn't impede the flow. So why might our results not have been completely accurate? Well, we selected shallower spots so we could stand in them, and these might have made the velocity readings seem slower than if we'd used deeper sites. And also the weather had been fairly dry just before we went, so that in some places the impeller hardly turned even though the water was actually flowing. However, using secondary data taken at a wetter time of year enabled us to reach a more accurate conclusion. When measuring angularity, as we've already said, we tended not to measure the boulders if they were too large, so angularity may have seemed smoother. What could we have done differently to make our results more reliable? Well, we could have used the dog biscuit method alone to measure surface velocity, as you could do this in shallower water. And we could have added our data together across the whole year group to reduce the effect of anomalies and have a bigger data set. And very finally, here are a few exam questions, so make sure you can answer all of them.